This is MYP5 Unit 3, and Chapter 1 is all about arithmetic series. Arithmetic with a stress on the met rather than arithmetic. So there's the question, what is the sum of the first 100 integers? So 1 plus 2 plus 3 all the way up to 100. What do they add up to? So one way you can do this is call that sum S. So S equals 1 plus 2 plus all the way up to 99 plus 100. But then you can write that series backwards. So S is 100 plus 99 plus all the way down to 2 plus 1. So that's the same thing, just written backwards. So you can add those two lines up, the one that I've written in purple and the one that I've written in sort of orange there, to get 2S. And then the interesting thing is that vertically, they all add up to 100. 1 plus all add up to 101. So 1 plus 100 is 101. 2 plus 99 is 101. And then all the way down to 99 plus 2 is 101. And then at the end, 100 plus 1 is 101. So you get lots of 101s added together. How many of them? Well, you get 100 of them because this goes from 1 to 100. So 2S equals 101 plus 101 plus 101, lots of 101s. 2S equals 101 times 100. We don't want to know what 2S's are, we want to know what S is, because we want to know the sum of this series. So single S on its own is 101 times 100 divided by 2, which works out to be 5,050. So you can very quickly and easily work out that the sum of the first 100 integers is 5,050 without having to actually individually add all of them up. In a similar way, the sum of the first 1,000 integers would be 1,001 times 1,000 over 2, because you'd have lots of things vertically adding up to 1,001, like 1,000 plus 1, 999 plus 2, 998 plus 3. You'd have 1,000 of those, so 1,001 times 1,000, but then that would be 2 times the sum of the series, so you divide it by 2. So that would be 500,500. So you can try and do that and spend more time on it and set it out kind of more like that one that we did previously. And you can see that it comes to 500,500. So that's an example of an arithmetic series. Each term can be obtained from the previous one by adding a fixed difference, which we'll call D in the terminology of this. So each term plus something gives you the next one. There's a regular difference between each term. So an arithmetic sequence has the following characteristics: a first term, which is commonly referred to as A, a last term, we use the letter L for that, a common difference, D, and then a number of terms, which we'll use N for. So in class we asked the question, in the sequence below, what are A, L, N, and D? So A is the first term, 13. D is the common difference, which is 2, because each term you add 2 to get the next one. In this case, the last term is 21, so L equals 21, and then N equals 5. There's 5 terms. So we saw how the sum of the first 100 integers was calculated from 101 times 100 over 2. And then 101, we got that from 1 plus 100. So that was the first term plus the last term. 100 we got from the number of terms, so that was n, and then divided by 2. So we can generalize that into a formula for the sum of an arithmetic progression, or AP, or arithmetic series. So that's S for sum equals n brackets A plus L, n times A plus L, all divided by 2. Sometimes for summation, you see the Greek letter sigma, which is a sort of almost a bit like an E or a backwards 3. So look out for the Greek letter sigma, capital sigma, used to denote the sum of things in this sort of work. Okay, so in class we said consider the AP 17, 25, 33, 41, 49. So the first term is 17, then the second term is 25 because it's 17 plus a common difference of 8. The third term was 33 because it was 17 plus 2 eighths. The fourth term was 41 because it was 17 plus 3 eighths. And then if you extend that argument to the 100th term, you can easily figure out is 809 because it's 17 plus 99 eighths. And the 1000th term is 17 plus 999 eighths added on to make 8009. And you can generalize that into a formula. So the nth term is whatever the first term was, A, plus the common difference, so it was 8 in this case, D, multiplied by 1 less than the number of terms you're on. So the nth term is A plus n minus 1 D. So we had some questions. Pause the video, have a go at those if you haven't done so already. So there's the first one. We had the first term, which was 5. We had a common difference of 13, so D is 13. And then the question was, find the 500th term, so n equals 500. So we stuck all of those into the formula for the nth term. Nth term is A plus n minus 1D. So the 500th term is 5 plus 500 minus 1 times 13. And then remembering to do multiplication before addition and brackets before multiplication, that all comes to 6,492 as the 500th term. Here's the second one. So the first term was A equals 131. The number of terms was 68. And then the common difference is minus 0.5 because it's going down by 0.5 every time. So again, you stick all of those into the formula and you get that the 68th term is 97.5. So if you didn't get that, just pause the video and have a look at the arithmetic. So we've seen two formulas. Sum of the terms is n brackets a plus l over 2, and the nth term is a plus n minus 1 d. In class there were some questions about my 1's and my l's, so that's an l in a plus l, but this is a 1 in n minus 1. So what if we wanted to know the first, let's say, 500 terms of a sequence, and we didn't know the last term? So to know the sum of the first 500 terms, you need to know the last term. So if you were given the first term and the common difference, but not the last term, what you might do is work out the 500th term as the last term from this formula, and then stick it into this formula. So I've written, if we don't happen to know L, we can calculate it using the second formula, but another way we can approach this is to substitute the second formula into the first formula to obtain a formula for S that doesn't need L. So if we don't know what L is, we'd work it out from this one, but you can just take this expression, a plus n minus 1d, and replace that for L in the other formula to get a general formula that calculates the sum of the first so many terms without needing to know the last one. So I've written, if the nth term is the last term, then we can substitute the a plus n minus 1d of the second formula for the L of the first formula. So we're taking the L there and then sticking in the formula for the nth term, assuming that that nth term is the last term. and a plus n minus 1d replaces L in that formula. So the sum of the first so many terms, n terms, is n plus a plus, and now it says a plus n minus 1d, all divided by 2. And we can tidy that up a bit and get it to the sum of the first n terms is n over 2 brackets 2a plus n minus 1d. So that's useful because it doesn't need to know what the last term is to work out the sum. Got to be a bit careful because it's got brackets nested within brackets, so you could lose track of things if you're not careful. So example, find the sum of the first 500 terms of this sequence. So we did that in class. So n is 500 terms. The first term, a, is 84. The common difference is 21, so d equals 21 because you're adding on 21 both times. So we don't know what the 500th term is, but that doesn't matter because we can just stick it into this formula. S equals n over 2 brackets 2a plus n minus 1d. And it comes out to be 2,661,750. And then we actually did a spreadsheet with 500 terms calculated and added them all up, and that did indeed verify that. I'm going to actually do that now. So here I am in Excel. I've got a first term of 84 there. I'm going to have a formula that takes the cell above and adds 21 to it to get the next one. I'm going to copy that down. So copy and paste it. So I've got lots of those. So I can paste that until I'm down to the 500th row. Nearly there. And then I'm just going to add them up by typing a formula in this cell that says equals sum of, and then just I can click on that whole column to say the sum of everything in that column and press enter. 2,661,750, which verifies what we worked out.